Hi everyone, and welcome to a new Submer webinar. This time we're going to talk about a dark science that goes under the name of thermodynamics. And I have here with me an expert that will explain a few things about this discipline and will also help us bust some myths. But we will talk about our guest in a moment, whose voice you've just heard. My name is Daniel Pope and I will be your host for this session once again. Sorry. Some of you probably already know me. I'm the CEO of Submer, a technological adventure that we started back in 2015 together with Paul Biles, my co-founder. My background is in data center design and operation, where at a very young age of 16, I started my first data center business literally in my bedroom. And you can imagine the challenges of cooling that. Probably it was back then when I started realizing the importance of running a data center business in a more efficient way. Or maybe it was the reaction of my parents when they saw the electricity bill that made them think, okay, maybe there's a better way. The data center industry needs to turn over a new leaf. This is obvious. And this is the one of the main reasons that pushed me together with Paul to create Submer. That was just in 2015, but I can guarantee you that in just 4 years, or 5 now practically, we've made huge improvements. And Submer has grown a lot, and liquid cooling has grown a lot along the way, and it's not a science fiction solution anymore. Our ambition is to transform traditional data centers into smart, lights out, immersion cooled data warehouses driven by robotics. Immersion cooling being just the first piece of the puzzle in those next generation infrastructures. If you want to get in touch, don't hesitate to reach out to me by phone, email, Twitter, LinkedIn, or whatever. You know that I'm always accessible. This webinar will, like all the others, be available on our YouTube channel, where you can also find all the previous ones. Follow us on social media to remain updated about Submer news. And now you can also find us on Applecast, Spotify, Simplecast, and SoundCloud. And we're waiting for a few more platforms to be online so we can also be on them. We've reserved, like always, 10 to 15 minutes of Q&A at the end of the session, together with our PR and communications manager, our lovely Mateo Mezzanotte, who is helping us organize all this. And we'll address as many of your questions as possible. Please type them into the Q&A section so that we can follow up later. And finally, without further ado, I'm delighted to introduce you to Jaime Pita, our esteemed special guest for this session. Specially esteemed because Jaime is our lead thermal engineer at Submer.
Thanks.
Jaime holds an MSc in aerospace engineering and specialist degree in fluid mechanics. Jaime started his professional career developing aero engines for ITP, which I think those components are used in quite a few of the engines that we fly in, right? Most of the airplanes are carrying turbines, if I'm not mistaken, from
Exactly.
ITP. You'll have to tell us a bit more about that later. He developed air-cooled solutions for radar and electronic countermeasures for fighter aircraft. In the UK, he worked for the environmental protection team in Rolls-Royce. He was also a team lead for aero and thermodynamics in Bombardier transportation. Jaime, welcome. Anything else you'd like to add?
Yeah, well, well, my background has always been in the aircraft and in the airline industry, right? Now we're here in Submer trying to improve a little bit more, right, the efficiency of the world. So yeah, quite happy to present this webinar to you guys.
Awesome. So tell us your secret. How do you get from making paper airplanes to immersion cooling?
Well, I got here to Barcelona because of love, mainly. No, but because of love for thermodynamics, I would say. No, the thing is, I found Submer's project very, very interesting, right? So I decided to get on board about a year ago, and we've developed a lot of things in the last year the efficiency of the solution has improved a lot. So I'm quite happy with the change from the aero engines, right, to the immersion cooling. I'm quite happy with that.
Okay, and I also know you're a sports freak because I know you're always attending our factory gym that we have.
Yeah.
Tell us a little bit about that as well. Come on.
Well, the thing is, my parents have always said that you have to rest your body, right, in order to perform better at work or at studies or whatever. So since I was a little kid, well, my passion is skiing mainly. So I put the skis on my first time when I was 3 years old only. And since then, yeah, I've been doing a lot of sports. I'm fanatic of diving, for example. I'm also fanatic of CrossFit and gym, as you have said. Mainly, yeah, any new sport that I can try, I will go for it as well. I'm a huge fan of sports. Well, one of my one of my little secrets is for example, I do not like football. I'm very bad at football, but that would be only it, right? There's no any other sport that I'm bad at. So yes. All right.
Great
So
stuff.
if you want,
I'm definitely handing it over to you,
yeah,
please.
let's talk about the thermodynamics, which is the main topic about on this webinar. So let's talk about thermodynamics. What is thermodynamics? Thermodynamics is a branch of physics, right? So we're mainly talking about physics that deals with heat, but also work and temperature, right? So those are main concepts that everybody knows, and the relation with the energy of the objects, radiation, physical properties of matter. So that's the reason, for example, we have these two images here, right? Where you can see the sun or warm colors. They're always associated with heat, right? But there's also blue colors here, which you always associate to cold, right? To cold elements like ice or whatever. So when I talk about physical properties of matter, that also implies that matter can change and substances can change in form. So in this case, when ice is forming, thermodynamics are involved in this matter change, right? So that's the reason it's not only covering temperatures, it's covering a wide range of things, right? So what is thermodynamics? I need to talk first about some concepts of thermodynamics. What is energy, right? Energy is one quantitative property that is in physics, right, that must be transferred to an object in order to perform work or heat at the object. That means this energy is inside every object in the universe, right? So it can be stored in objects, but it also can be transferred in objects. So for example, if you pick up a book, you know, and store the book in the bookcase, you're basically storing it in a higher tray on the bookcase. You're storing it with more potential energy, for example. Or for example, if you kick a ball, right, playing football, you're transferring kinetic energy to that ball, right? So that's a physical property, right, that can be transferred from an object to another. Another example would be, for example, when you eat food, that food has energy inside stored that is being transferred to your body, right? So that's the first myth busting here, is that energy can be converted in form, but cannot be created or destroyed. So it's a thing that is in the universe, and it's always present in the universe. You cannot create it or you cannot destroy it. So this myth busting is related with the fact that there's people, for example, that think that the heat disappears, and it's not disappearing ever. Like never is disappearing, right? It's being transferred to a different state. That's the reason, for example, I've put this image of the roller coaster. A roller coaster is working in that way. So it's storing potential energy by means of the height of the roller coaster, and then it's transferring it to kinetic energy. It's the same way of storing the energy and then losing it, you know, with the kinetic energies is just transforming between one way of energy to another.
So I can put that in a different context. All that heat that data centers release into ambient air,
Mm-hmm.
what happens with that? Where does that go?
Exactly. So it goes to the environmental layer, as you said. But the thing is, the main efficiency increase in the smart pods or in the smart pod system, right, is that we're using less energy applied to the system to extract that heat. So the heat is more or less the same. If we're talking about 50 kilowatts, that's the nominal thermal power for one smart pod. You're always going to transfer this heat up to the atmosphere, but you're going to use so much less power, right, than a traditional air-cooled data center. That's it. So this is the main improvement, but the heat does not disappear inside the smart pod. That's what we want to, that's a message we want to send to the people, right?
Yeah, thanks, Jaime. And I know we're going to dig into, this is just an intro so that we can dig into the application of thermodynamics in our solution. So please continue.
Yeah, so yeah, exactly. I want to refresh concepts to the people here. So let's talk about temperature. Temperature is a way of measuring this energy that is stored in objects, right? So it's a physical quantity that evaluates the energy of an object or a substance, something that is inside the objects, right? Or the substances, the atoms, right? So it's highly related to movement at a molecular level of the substances, right? And it can be seen between atoms in a molecule, right? But also between molecules themselves. So in a solid, for example, we will see an increase in temperature when exciting these atoms, right? But for example, in a gas or liquid, you would see that it increases the temperature by moving these molecules faster, right? But this micro movement is always present. So it's present in your body, right? In the atoms of your body. When your temperature rises, you could see these micro movements, right? So it's another form of kinetic energy. That's what I said here. Some of the concepts that we must refresh before that is work. What is work? Is the energy transferred from an object to another, right? But means of an application of a force. So for example, here we have these wind turbines, and the wind is performing work over these wings, right? And that work can be transferred to a different type of energy, which is electrical energy in this case, right? So it's worth mentioning that this energy or work is measured in joules, which is the energy unit in the international system. And let's talk about power as well. Power is the amount or the rate of energy transferred per unit of time from an object to another. All right, so it's measured in watts, and watts is joules per second. So it's the rate of work performed per unit of time, right? So let's go to the next slide, because you would see, okay, then heat is another concept for thermodynamics. What's heat? Heat is also an amount of energy. Sorry, heat is energy, a different form of energy, okay, that can be transferred from an object to another by means of thermodynamic mechanisms like conduction, convection, radiation, etc. Right? And you can see here that the heat, right, in this energy form, its unit is a joule, which is exactly the same, right? So there's a misconception when we're talking about heat, because people talk about heat when they're talking about the amount of energy transferred per unit of time. So it should be called a rate of heat transfer sometimes, because there's people talking about thermal load, right, which is expressed in watts and so on. But they're basically talking about the energy transfer per unit time, right? So it should be called rate of heat transfer. There's a misconception with this concept a lot of times. All right. So you would say, okay, this is the joke. Work and heat are the same, and yes, they're exactly the same, because both work and heat are forms of energy transmission. And for example, if you've been playing paintball with your friends, there's a funny fact. When a paintball does not explode in your body, sometimes you feel that it's, you know, more painful than the ball that actually bursts, right? And that means because when the ball is hitting you and it bursts, the kinetic energy is released. But if it's not bursting, you would feel a lot of, you know, pain and burning in your body. That's kinetic energy being transferred, like, you know, a thermodynamic with a thermodynamic effect. It's burning you, right? Or if you slap someone in the face very, very hard, you would feel that it burns because both are forms of energy. Okay, let's talk then about laws of thermodynamics. So there's 4 laws of thermodynamics mainly. There's the first, the second, the third, and then there's another one called the third law. And we're gonna cover these 2, the first and the second. So the first is stating basically that the change in internal energy, so the energy stored in objects of a system, is equal to the difference between the heat supplied to the system and the work done by the system. So if we go back to the wind turbines from a previous slide, right? So the wind was performing work to the wind turbines, but we can imagine these wind turbines as a thermodynamic system. So the wind turbine could actually move the air performing work to their surroundings. That's it. So this means that an isolated thermodynamic system would increase this energy with this balance. It's always going to be a balance between heat applied to the system and work performed from the system to the environment outside it. All right. And then there's a second law of thermodynamics, which says, okay, if you have two isolated systems, right, thermodynamic systems, which are completely in equilibrium inside them, right, and then if you merge them together, they're going to achieve a new different state, which is in the middle of them, right? And it also adds a variable called entropy, which says, okay, there's always going to be a loss of energy in this process, right? So nothing's irreversible. That's it. That's what's always been happening in the universe. That's the reason the Big Bang exists and everything, because the universe is in constant expansion and the disorder is growing more and more and more. That's the thing. And then there's the third law, which I'm not going to talk about, which basically says that the more you approach, the 0 Kelvin point, the entropy becomes less, which is basically impossible. And then there's the third law, which is basically talking about temperature. So this is a little, diagram talking about these two things. So if you want to go from state A to state B, you have to carry on, you have to apply heat loads on the system, and then the system could perform work out of your system. So that's gonna imply a change in internal energy to state B, and internal energy is related to temperature, as we have seen in the previous slides, okay? And the second law of thermodynamics can be expressed as this, 3 balloons diagram, which says, okay, you have an isolated system A in a thermodynamic equilibrium, say, for example, a glass of water, and then you have another isolated thermodynamic system called B in another different state of equilibrium, say is a bucket of ice, and then you merge them together and you have a different state for both of them, all right, which compose the same, or now the new domain of calculation, and then introduces entropy to the system. I don't know, probably these concepts are a little bit rough for you guys.
I have to say, it reminds me of my worst times in physics class. I mean, we got the basics of thermodynamics, and for sure, if you still have doubts, worry not, because this webinar is going to be recorded and available on our website and YouTube channel. But now let's talk about how thermodynamics principle applies to the Submer technology.
Perfect. Yes, let's talk about that. So yeah, all of these laws that I've spoken about before, how they apply to the SmartPod units that Submer is developing, right? So the SmartPod units are basically thermodynamic systems in equilibrium, right? We have designed them to be in equilibrium, in fact. And the heart of these machines is basically the liquid that Submer has developed, the smart coolant, right? So the thermodynamic element, the main thermodynamic element here is the liquid. And we have designed it to follow the first law of thermodynamics here. So we have this system, okay, the tank, for example, this is a small one or the big one, and it has internal energy on it. So by applying heat loads to it and also performing work or no, as you can see, the work here is going to be probably zero. By applying heat loads to the system, we're going to drive it to a different thermodynamic equilibrium. And that's what we basically call in Submer set point of the machine. Because at the end, we're basically looking at, okay, what temperature are we going to drive this tank, you know, in order to guess what's the operating temperature of the chips, right? So it's in complete equilibrium all the time. Myth busting again. I'm recalling the energy myth busting that I spoke about before, is that the thermal power that we apply inside these tanks will never disappear. It's transferred to the ambient temperature. The thing that the main improvement is how is this transfer out, right? So yeah, I have made a couple of diagrams here to explain you guys how is this working. So imagine that this little sun is the service that we have inside the SmartPod, right? So it's generating heat, right? Because electrical power, it's historically very inefficient. So electrical power can be more or less transferred to thermal heat load, you know, to the environment, which is usually air. But in this case, yeah, we decided to put this service into liquid, right? So what's the liquid doing? The liquid, it's basically extracting the heat from the service, and that's by means of a very basic concept, which is called convection, right? So it's exactly the same as when you, for example, have a hot coffee cup in your hands and you blow it, just to take the heat away. So the heat, the fluid flows are extracting the heat, and then they go through one of the main things in the tank, which is here in the left, usually, and has a pump. So there's a fluid circuit here that's taking the fluid out of the tank, you know, and driving it through a heat exchanger, right? And this heat exchanger is driving the heat out to what exactly? There's a water loop, right? So in order to prevent well, we want to have the smart coolant liquid inside the servers and not, you know, going out and back to the data center warehouse. That's the reason water is easier to manage in this aspects, right? So we're transferring the heat out to a fluid loop of water. This unit here that I have spoken about is a CDU, a cooling distribution unit, and that's where the exchange is performed with this cold water. And in summary, at the end, these units are always, you know, balancing and reaching new thermodynamic equilibriums. So for example, if we put more thermal power to the service inside, then it will reach another different state. Or if we place the Submer SmartPod in a different room with different conditions, it will reach another thermodynamic equilibriums. So at the end, it's a constant succession of thermodynamic equilibriums, right? Between this SmartPod and the environment where it's placed.
So maybe Jaime, you can give us a bit of an understanding of how do we because compute does not operate at constant compute processing intensity, right? Servers vary their consumption, especially during business hours, for example, versus night hours. How does the SmartPod regulate that?
Okay, yeah, that's a tricky question. Not a tricky question. Thing has to be related with this. So imagine that the variable work, well, actually the variable work is not in the SmartPod system. There's a little bit of work applied to the system, which will change the sign on the equation, which is the pump inside the SmartPod units. But it's basically negligible when we're talking about thermal power applied with the servers. And the thing is, as the servers go up and down in thermal power applied, then it will imply a change or another thermodynamic equilibrium in this term of the equation, and that means temperature, because we're gonna see this in detail in a few slides, right? The equation that is driving this, but it's basically a different state in temperature, right? And the thing is, the smart coolant is capable of absorbing this heat because it has more specific heat than air, for example, and hence the inertias of the tank, I would say they're way too high. So you can apply more thermal power to the tanks, and it will take more effort for heat the tank up. So it's going to remain more or less at a stable temperature. We've seen that the smart coolant could be resistant, to thermal power changes. So it's going to absorb even more than air. That's more or less the answer to that question.
Yeah, and I guess in my way of describing it would be that the CDU needs to vary the amount of energy it's extracting from, so the amount of heat and energy it's extracting from the tank in a variable way, which is how the system is designed to keep that equilibrium, that set point.
Exactly. Yeah, that's
I'm learning something. This is great.
That's an additional feature, exactly. So we also have some regulation here as well. So the fluid is actually dumping, this thermal power changes, but also we can regulate the system by means of the CDU. So it's always, a game of balance between parameters here. That's the thing. Okay, let's carry on then. So then where does this heat go? This heat is always going outside to the environment, and that's why we're using cooling towers here outside the data center to extract this heat, to the ambient air. And so then you would say to me, okay, what's the improvement? I've been talking about this before, and that's the reason I put this quick analogy. Both systems are using fluid to operate, because the air for you guys is mainly a fluid. The air is exactly the same. It's only imagine the air as being less dense fluid than the smart coolant, or for example than water, right? And the traditional way of cooling servers is with air, right? With busting, yes, the air is a fluid. So in fluid mechanics, we usually study air as a compressible fluid, and water and some other liquids, we're studying them as incompressible fluids, right? The main difference between these two features, right, the SmartPod tanks or a traditional air-cooled rack, is that the SmartPod is using these fluid loops that I've been talking about before to pass the energy into the air. And the traditional air racks do not air any fluid loops in here. They just use fans, to take the air of the environment and directly extracting the heat out. But that means is they're gonna use hundreds and hundreds of fans inside these servers. So that's a lot of energy. Whereas in the SmartPod, we use a pump, just a pump. And with a pump, we're capable of extracting the heat to the water loop here. Again, so what's the improvement with this? The main improvement also comes with the fact that the smart coolant is a liquid, and the air is a gas, which is another form of a fluid, right? But air traditionally is a substance that is insulated, and that's the reason I've put this tiny coat here, because what's the example here? What do you do, for example, in winter? We're getting closer to winter. When you want to stay warm, you just put a coat. Because of what? Because the coat is made of air, right? So the air is insulating traditionally. or for example, another way of looking at this is, double glazed doors, right? They're used to keep the rooms cold from the outside environment, for example, right? So that's a climatic element on the houses. So air is super insulated, and it's probably one of the worst elements we have on Earth for cooling down things. But then we have water on Earth, right? What is one of the best? Well, it's reflected on its specific heat here. We're going to talk about a specific heat here. But it's impossible to use in the SmartPods because there's a risk, obviously, of destroying the service. And that's the reason we came in between and we developed the Smart Coolant, which has more or less a specific heat which stays between the two elements, air and water. So that's fine. The good things about the Smart Coolant V3 is that it's completely dielectric, so there's no risk of a short circuit inside your service, for example, right? And what's the specific heat? Remember the first law of thermodynamics we've been talking about? So when you actually develop the equation a little bit more, there's a term here which is talking about temperature difference from the state A or 0 to the final state. And then there's the mass of substance that is storing this energy. And then there's the specific heat, which is basically a parameter that's saying you, okay, what's the amount of heat that I need to heat up a substance by 1 degree, per kilogram of matter in this case. So the higher this parameter it is, it means that for the same thermal power applied with 0 work applied to the system, the highest is this parameter, you're going to have less temperature, right, on the system at total. So that means we're gonna be able to absorb more energy inside the Smart Coolant just for the fact that that is more dense than air, and it has more specific heat. Okay, just stop me if you if you need more explanation on some concept, Danny. So that's the main improvement on an overall, on a system basis. But what if we go to the deep detail, right? What's happening exactly at the server level of it? What's the local improvement? We need to understand or identify the main heat transfer mechanism that is occurring on a server, for example, on a chip, right? So historically, we have 3 mechanisms of heat transfer in thermodynamics, which are conduction, convection, and radiation. And there's no need of an explanation with an equation for this, but with a funny image, that's more than enough. What's conduction? Conduction is the mechanism of transferring heat and so on, energy, from one solid to another solid just by means of touching one solid to another. So in this case, just forget about the fire and imagine what's happening inside the pan when you fry, your mushrooms and your food. What is happening is energy is being transferred from the pan to the food by contacting it, right? So it's basically going from atom to atom. What's convection then? Convection is the second mechanism that we have for heat transfer in the nature, right? And that's basically extracting or applying heat by means of storing this heat on fluid particles and then driving the particles away from the system, not the system. In this case, this pan over here, right? So imagine that it's hot. So this heat is being extracted by the surrounding fluid, and then as the fluid is free to move, it can go and hence, drive the heat away from this element over here. And then there's another way of transferring heat from one object to another, which is radiation. And you can see radiation everywhere in your day basis routine, right? Radiation is a mechanism for heat transfer, which is relying on electromagnetic waves. And hence, we're not gonna look into any detail of radiation because normally SmartPods are, stored in a warehouse. So we, for example, we're not We're not putting them under a solar load. So how can we act to improve the chip performance, right? We can act on convection. That's what we have seen. So because this is the main mechanism that we can have inside the SmartPods to extract the heat out. We can act a little bit on conduction, I would say, because it is always a combination of conduction and convection, extracting the heat from electronic elements. But for sure, we are not gonna look into any radiation on this system. So we're gonna try to maximize inside the SmartPods the convection mechanism, and also we could act into the conduction mechanism by only with help from the server manufacturers. And what's the reason for that? The reason for that is we want to improve this convection, right? This convection mechanism, and the equation that is driving the convection mechanism is this one, which is called Newton's law of cooling. And it has been historically demonstrated that air, which is marked in red, right, has less capabilities than water and liquids for cooling, just because it's less dense than these two elements, right? The liquid elements, liquid fluids. And there's a parameter inside this equation which is called heat transfer coefficient here, which is actually more or less the same as the specific heat did, right? And you can see here that for air, gases, and dry vapors in free convection, this parameter is very, very poor, whereas in liquids, it's very, very high. So that's a reason, another reason to trust on the smart coolant liquid, because this parameter is way high than the surrounding air for extracting heat, right? Okay, so we have been working extensively on the heat transfer coefficient. We've been doing experiments for the past months, and we have found numbers. Now we have numbers for the smart coolant in natural convection and in forced convection as well. And we have seen that compared to air, which is more or less in this zone over here, which is very, very geometrical, but that's because there's a lot of unknowns on the heat transfer coefficient. It also depends on the shape of the object. It depends on the surface of the object, the rugosity, a lot of things. There's a lot of parameters, but it's more or less in this area, located in this area over here. And we've been doing studies on smart coolant in natural convection. We've been doing CFD studies as well. And we've been doing studies on forced convection, which basically means accelerating the fluid to improve this parameter over here. What we have seen is that we have 5 times the capabilities of extracting heat with smart coolant in natural convection. And we have more or less double the capacity in forced convection, but it's still, we have to explore a little bit more. What would this imply in local temperatures, in hotspots of service? If we improve this parameter over here, then that means that for the same amount of thermal power applied, this parameter, the temperature of the chip, is gonna decrease. So you're gonna find yourself in this particular case where the temperature of the chips are operating at a lower temperature than in traditional air-cooled solutions. That's it, more or less. Okay. And how do we apply this to the SmartPod? We're applying this to the SmartPod by distributing, right, the fluid up to the surface. You can see there's a live image here that we have made by means of CFD, but also we have tests done or carried out with the units. And you can see here that the maximum temperatures here are 320, right? Kelvin. This is Kelvin, not Celsius. This is Kelvin scale. So we have observed local temperatures between 60 and 70 degrees with set points of 45 degrees Celsius on the smart coolant, right, on our tanks. And comparing this to air, if we're talking about air at 45 degrees, you can see that the GPUs and CPUs more or less reach 92, 95 degrees Celsius, which is basically a very, very high number for this. We're staying at this point with immersion cooling. And still, we have a lot of work to do, because what if we accelerate even more, right? The fluid. We're going to be capable of extracting heat more efficiently. And when I say more efficiently, we're talking about temperatures in a chip level. So that's it. More or less, the sky is the limit at this point, because we've been developing a lot of things throughout the year, and now we're moving forwards to this accelerated smart coolant scenario. And the way we're doing it in the thermodynamic team here in Submer is we're always looking at the theoretical definition of the problem. We're doing CFD validation, and then we're doing testing and post-analysis with thermocouples, with volumetric flow, rate sensors. A lot of things are in our hands, to improve the solution. We're constantly looking for improvements, right? We've been testing extensively this heat transfer coefficient. You can see here this fancy image of one of the test rigs that we have for the smart coolant. And the main challenge now is basically to start conversation with server manufacturers in order to optimize the chip and heatsink system, right? In order to modify all of these electronics that have been designed for air cooling solutions, which now need a change in paradigm and say, okay, now we're going to store these servers inside liquid. So we need a change in concept in order to improve them up to the utmost, right? And that's more or less it. It is always about balance, as I said before, but there's a long way before, a long way in front of us to explore yet. So
yeah,
that's it.
I thank you very much, Jaime. That was really interesting. I mean, I've seen you guys run some of your tests where you're able to extract 4, 6, 8 kilowatts of heat from a single server U with an optimal immersion design. That's, I guess, where the sky is the limit, is where we can align the magic of the smart coolant with the server manufacturers that are already embracing the technology and thinking how to leverage this in their future roadmaps.
Yep. Yeah.
So we have an interesting path ahead for sure.
Exactly.
Okay, so I guess let's see if we have some questions from our guests, which we do. I have one here, which is, what's the difference between Submer immersion solution and other liquid cooling solutions using the same convection principle?
Okay.
And I guess this might be related to the actual flow being forced, I imagine, in our tank versus some other solutions on them.
Yeah, could be, but they may be thinking on change of pace. I don't know. That's very hazy, the question, but yeah. Well, I would probably jump in and explain something. Yeah, the difference between the Submer immersion cooling solution is single phase, right? So we've not talked about, if you remember the first slide, I was talking about ice and change in substances. There's another way of liquid cooling, which is two-phase immersion cooling, and that's relying on the fact that when you change the properties of a substance, so if you change from liquid to solid, for example, there's a thermodynamics mechanism in between, which is called latent heat, right? In which there's no change in temperature, and you're basically investing this heat exchange in the change of substance. So that will be one of the main differences between our solution and the two-phase immersion cooling. And if they're referring to another liquid cooling solutions, which are probably using forced convection. I would say that our solution is more or less a mixture between the two of them, because we found that, yeah, there's a lot of natural convection inside the tank, but we also have the distributor on the bottom of the tank. So we are exploring new ways on how to drive this fluid flow to the chip, directly to the chip, right? Not directly, but by means of obstacles or something, in order to blow more fluid into the hotspots of the system.
Precision cooling, let's say.
Yeah, exactly. But as I said before, there's a long run until we reach that point, because every server is different, every GPU is different, every heatsink is different. So there's a lot of combinations, I would say. There's infinite possibilities of doing the same thing.
Yeah.
The thing that I can say is we're improving the tanks up to the limit, right? So, well, you would talk about that later, where we have new things coming on very, very quickly, and we have applied some of our studies to the SmartPod units to make them more efficient. And now, for example, we know that if you want to store a GPU inside the tank, we have to talk with the server manufacturers to put the GPUs in the bottom of the tank or closer to the bottom, because that's where the main flow is coming in, right? And in order to, scratch a little bit more of temperature out of the system, that's it. Yeah.
Thanks. We have another question here from Moses Levy. Have you done an analysis to understand the PUE improvement using liquid cooling technology? I mean, a data center using conventional cooling versus liquid cooling. And if so, can you expand on the values? That's a really good question, and it's actually one of the first things that we set out to do was to deploy a full production system at a third-party certification authority. So actually, we leveraged A+, which is a well-known German certification authority, because one of the challenges we had when we set out with our technology was a lot of people not believing that a full system would be capable of delivering the PUE that we said. When we sat down with the data center engineers, I guess they scratched their heads saying it's impossible that this is capable. So we said, well, like, we can obviously deploy a system and measure it, or we can certify the efficiency with a third-party authority, and you can believe it, I guess. So that's what we did, and the results, and I'm very happy to share those certifications offline, of course, was that a full immersion system measured over the period of 6 months delivered a PUE of 1.02. We typically claim 1.03, but I mean, it all depends on the efficiency of the pumps. There's some very minor variability there, I guess. But that's what you can typically expect for a data center, which is specifically designed and built from the ground up for immersion cooling, which means that you have closed water loops, dry coolers, and that you're operating the fluid at, I guess, higher temperature ranges that really allow you to run on dry cooling technology for all year round. I hope that answers that question. There's another very good one here. What is the future of immersion cooling? So then this one's from Himanshu Guru. And there I would connect it probably with what Jaime was kind of alluding to. We believe the future of immersion cooling is precision immersion cooling. And precision immersion cooling is probably an optimized application of the open tank environment that you see today, meaning we think that specific placement of the chips and directing the fluid to specific areas of the servers where it makes, where the heat is generated, is going to allow us to deploy much denser systems. In the same way, we also think that, and these are some of the solutions that we're working on and will be bringing to market, that it is possible to take the best of immersion cooling together with the best of direct to the chip cooling and combine them in a way that you have a scalable solution which leverages the benefits of using immersion dielectric fluid, but where you can still envision traditional vertical racks. So I think that might allude us to the direction that we see things going in. Another question from Todd Alexander. Do you have switch PDUs inside the tank? Do you typically then plug the tank into a UPS for critical backup power if the standard power grid goes down? Very good question, Todd. So we typically do not deploy the PDUs inside the tank. The PDUs are deployed on what we call dry zones on both sides of the tank. The reason is the PDUs as such do not generate too much heat, so it really doesn't make much sense to submerge them. We're very fond of environments without PDUs, like open compute hardware environments, so OCP equipment, where we have the benefits of cable-less, or being able to leverage cable-less power distribution, which is obviously a nice win in immersion cooling. Do we typically plug the tank to UPS power? We don't, and this is one of the reasons why we don't, is because of that thermal inertia that Jaime was referring to. The tank can store a lot of energy before the chip temperatures raise to temperatures where it could be critical for the systems. So the typical switch between UPS power when you're waiting for the diesel systems to kick in, we don't need to connect the tanks to the CDUs in this specific case to UPS feed. It doesn't make much sense because a couple of minutes are absolutely fine. And actually we have detailed analysis that we're also happy to share, where if you actually don't have a functioning CDU for up to 30 minutes, the system is capable to withhold the temperature or the energy being stored in the fluid during those 30 minutes, meaning you don't need primary cooling for 30 minutes, or you can live without primary cooling for 30 minutes.
Yeah.
Which is actually like in the, if you have a critical situation where a CDU fails and you need to replace it for some reason, you actually have those 30, 40 minutes of time to unplug a CDU from its quick disconnects, pull it out, replace it with one that you have on site, and you're up and running again, which is a process that we've designed to do in less than 5 minutes. Okay, I mean, there's quite a few more questions. We'll definitely follow up with them offline. But for the sake of time, I'm going to leave it here for the Q&A. Once again, if you want to be updated about Submer's news, we suggest you to subscribe to our YouTube channel and follow Submer on our social media. I would also like to remind you about our white paper, The Convection Principle, written by the one and only Jaime, who you've had the pleasure to speak with today. And also don't forget about our ebooks and use cases around immersion cooling and smart data center technologies. They're all on our Learn section of the website. And also allow me to remind you about the upcoming OCP Tech Week, which we are members of and will be presenting from the 9th to the 13th of November. Specifically on Tuesday, the 12th of November, our CTO, Scott Noteboom, will lead a presentation, which for us is very exciting. This presentation is named Reference Design Proposal for an OCP Blind Mate Network Backplane. And it's really about tackling the challenge of how to get rid of network cables in the rack. And we have a very specific purpose for that we'll unveil at the presentation. And the registration can be found at the link here on the OCP Tech Week page. And last but not least, stay tuned, because on the 2nd of November, we're presenting a new product, which we think will change the rules of the edge and cloud computing game. Yeah, you can see a bit of a Halloween teaser done by one of our web and graphic designers, Dario. And that's all. Thank you very much, and see you next time in our upcoming webinar.
Thank
Stay
you.
safe.
Cheers.